2021. And then module 4 and 5 and 6 are the design of the steel member itself. So we will have design of steel member subjected to tension forces, compression forces, shear and bending moment, and combined action. And in module 5 and 6, we will be designing the connection and the portal frames. Okay, and the textbook we will be using is these two textbooks, which are available online, so you can easily get them. And again, this is the Australian standard we will be using, the steel structure standard. And 1170.0 is for the structure design action, like load combination and so on. And we have also 1170.1, which includes permanent and imposed loads, like dead loads and live loads. And finally, again, we have the wind load standard, which 1170.2 version 2021. Okay, and also we'll have some capacity tables of steel, like the properties of the steel structure section and so on. So this can be found under OneSteel and also the Australian Steel Institute. Okay, so let's now go through week 1. So in week 1, we have some topics. So the topics we have is introduction to steel structure and structure steel framing and other steel structure elements. The objective of this week module is to know the function of steel structure and different construction material used in industry and the advantages of using steel structure over concrete. And we will have to know about the development of steel structure, and we will know also some key concepts of selecting the structure steel elements. And we will have some structure systems of mill type and low high rise buildings. And then finally we will know when to use the blade girders in long span structure. So firstly, in the introduction of steel structure, what is the function of structures? So the function of structure is to carry and transmit the loads in various ways in multi-story building, like the wind load, the loads we can have is wind load, snow loads, and rain. Wind load resisted by external walls, so we have wind load on roof and wind load on walls. And also we'll have dead load and live load. The dead load is the own weight of the structure element, and the live load including people, furniture, floor covering, machinery, and so on. And all this load should be transmitted to the steel frame and finally to the foundation. Okay. And we have different structure based on their function. So we might have bridges, supports dig, allowing the passage of pedestrian and vehicles, dams to hold back volumes of water, retaining walls to prevent slippage of embankments, offshore structure like carry drilling rigs, accommodate crews and helicopter beds and so on. And also we have harbor docks and jetties, carry cranes and resist the impact of docking ships. So we have various types of structure as well. Also, for the construction materials, we have steel, our focus in this course. So steel is one of the most used material. We have mild steel, low carbon content. So the mild steel is low carbon content, which is strong, cheap, ductile, and can be easily welded and widely used. The other type of steel we have is high strength steel, which is higher in carbon content. It has greater strength. It has greater strength but less ductile. Can you still see my screen? So I don't know what happens here.
Yeah.
Okay. And also, again, sorry, the high strength steel, high carbon content, greater strength than mild steel, but less ductile. So the problem of high strength is less ductility than mild steel. Okay. The advantage of steel, it is like has a quality control, high quality control compared to other material. So we have low variation in probabilities. One of the disadvantages of steel is weak resistant to fire and also the problem of corrosion. And we have two types of steel sections, hot rolled steel and cold formed steel. And later we will know the difference between both. And the second most used material is the concrete. So it is a mixture of cement, water, and coarse fine aggregates, cheap compared to steel and also widely available. So the advantage of concrete over steel is price or the cost. The concrete is higher versatility, so it can be cast in situ and it can also be formed using formwork. The problem or the disadvantage of concrete, it has weaker or less strength to weight ratio compared to steel. And also another drawback is the tensile strength of of concrete is only 10% of its compressive strength. So the tensile strength of concrete almost 10% of its compressive strength. One of the advantage compared to steel is the concrete has good resistance to fire and very durable. For timber is naturally produced material, but the problem is it has a variety on the quality and the defects. The timber normally stronger in tension and than in compression due to the nature of the grain. So for timber, the tensile strength is more than the compressive strength. Hardwood, short grained, not necessarily hard. Softwood, long grained. So we have two types of wood, hardwood and softwood, based on the grain. Some of the disadvantage we have in timber is warping and twisting can be eliminating, but can be reduced by using it in laminated form. So one of the problem is warping and twisting, which can be overcome by the laminating form of timber. Treatment is required to resist the fungal attack in timber. So that's why we have seasoned and unseasoned timber. Okay, so this is just a brief introduction of the materials available to go through the steel later. Okay, so one of the material also used is masonry. So the masonry is bricks or concrete blocks. The masonry is brittle and weak in tension and mostly made of clay shell. The engineering bricks can be the main load-bearing component in some masonry structures with minimum guaranteed strength. So in some structures, the bricks can be a main supporting element. And also we have some like decoration or facing bricks, so have different strengths with a better appearance. So there is a difference between the engineering bricks and the facing bricks. One of the material we have as well is aluminum. Aluminum also is a metal. So pure aluminum is obtained from bauxite. They are often expensive to produce and also soft and weak. So they are expensive, soft, and weak. Magnesium is added to aluminum to strengthen it. The aluminum generally has high strength to weight ratios, and also it is ductile. So one of the advantages it is ductile. Fabrication of lightweight roof structure and window frames. So because of the lightweight of aluminum, it can be used for lightweight roof and window frames, which is the most common application it has. And also the aluminum can be extruded into more complicated sections. The last material we want to know or about is the composites material. So composite material like fiber reinforced polymers or composites, or glass reinforced plastic, carbon fiber reinforced plastics. All these are types of composite material. The first one is FRP, and this one also GFRP. These are GFRP can be used as alternative to steel reinforcement now. So these are new materials that can be used in construction with better or modified properties. The composite material can be also used in aircraft, automobiles, and also the buildings. The disadvantage of this material is expensive and not fully understood because it needs more testing. So it's still under research. Okay, you can watch the video showing the hot rolled steel versus the cold formed steel process using this link. The next topic we will have is the development in steel structure. So how the steel structures developed. So the early steel structure were fully exposed and riveted connection without treatment. This was the earlier use of it. The form of structures was driven by its function. No special consideration was given to aesthetics. Rule of steel changed with time towards lighter envelope and larger span. So with the development of steel, we look for lighter and larger spans. Structure framing exposed to full view has take many forms like space frames, parallel vaults, cable stayed, and cable net roofs. High visibility of structure framing desire more aesthetically pleasing connections, and cost is kept down through well-designed connection and simplicity of drawing and maximum possible repetition. So to reduce the cost, the connection need to be well designed, and we need to have like simple detailing of the structures elements, and we need to like maximize the possible repetition of the details and the design. Structure framing becomes more attractive in terms of cost, reduce fabrication efforts, and increases the quality and the engineering efficiency. So basic understanding of the behavior of the structural steel and the use of design or modeling would have enhanced the efficiency of the design. So we need to understand the behavior of steel to like optimize the design and reduce the cost. Design standard plays an important role in this aspect. So the standard, again, 4100 will play important role to understand the the structural steel behavior and improve the efficiency of design. These are some structural steel works. So all this building are made from steel structure or steel work structures. And the definition of steel work or structural steel work is an assemblage of commonly used standard steel section connected by bolts or welding or combination of bolts and welding. Like for example, if you know that we have one of the most common section is I-beam, or in Australia, universal beam or universal column. So the shape is I, and also we can have like channel. So these are some of the most common used steel section. So one of the example here is the HSBC Bank in Hong Kong and Petronas Twin Towers in Kuala Lumpur. And the Sydney Harbour Bridge in Sydney and the Golden Gate Bridge in San Francisco. These are two bridges here. These are like tall building or multi-story building, tall building. And this also like multi-story building. So we have two bridges here. So this like traditional building or normal building. And here we have like some extra or not like uncommon building, which is cable knit roofs, also made of steel. So you can see steel structure here, and this also some steel structure beams. So this is cable knit roofs. And also we have a space frame structure also made of steel. So the steel can be used in all these type of buildings. Now we jump to the steel as a structural material and what is the advantage of steel to be used as construction material. So the steel is widely used as structure. Why is the most used structure metal? The advantage of steel is its great strength and good ductility. So it has point of high stress. At the point of high stress, the material yielding enable load redistribution. If you know the stress strain relationship of steel, so you can notice that the steel doesn't break at the yield strength here and still can deform after the yield. So this give it high ductility. Also high stiffness. The steel has high stiffness. So this causes a small deflection of the elements. Also the steel structure members are easy to fabricate and good quality control because it is made or manufactured in factories. So it has good quality control, ease of alternation and extension, ease of and the speed of erection because it has like connection. So for example, this is a connection. So it is easy also to install or erect, and also the steel is relatively cheap with the properties it has. Okay. Do you have any question, guys?
No.
If you have any questions,
No.
just let me know, please.
Not clear. Thank you.
Thank you. So the next, I just have a message. Thank you, William. Okay, so the next is the comparison between steel structure and concrete. So as you know that concrete is the most widely used material in construction, so that's why we need to compare steel to concrete. So steel is roughly 3 times denser in concrete. So if you see the density of concrete, raw concrete is 2,400 kilogram per cubic meter. For steel, it is 7,065 or 85 kilogram per cubic meter. So you can see that the steel is 3 times in weight or denser than the concrete. But for a given load carrying capacity, comparing steel to concrete, so the weight is 1 to 3. So if you want to design same member to carry same weight, so if you need 1 of steel, so it will be 3 in concrete. The volume, if you need volume 1 in steel, so it will be 10 times in concrete. The cost, the problem is the cost. The cost of steel is 4 times the cost of concrete. So the cost is the problem, but for the weight and the volume, the steel is much better. So concrete is preferred for structure when dead load doesn't dominate. For example, weight walls, floor slabs on ground, and suspended slabs, because it is heavier. So if the dead load doesn't dominate the design, so we can use concrete. And also if you need heat and sound installation, because as you know, concrete is better in heat and fire resistance. So that's why it is preferable here. So the steel, for steel is generally preferable in over concrete for long span roofs and bridges. So for long spans, because the stresses will be high on steel or on the structure, so it's better to use steel for long span roofs and bridges. Also in tall buildings and moving structure where weight is not favorable, so you can use, or you have to use steel. Steel is oftenly used with concrete, not only in reinforced concrete, but also in composite steel concrete construction. Okay, standard steel beam supports reinforced concrete slab are connected by shear studs so that the steel and RC slab behaves as a single structure unit. So for this one, to explain this one here, if you know the composite structure, one of the common one is you have steel section or steel beam below or supporting a concrete slab or a reinforced concrete slab. So this is what is meant here by composite construction. So to connect the steel section to the concrete slab, we have this red element, which is called studs. So this a type of construction where the concrete is used with steel in composite steel and concrete structures. In extreme cases, when weight to be minimized, we can use aluminum or magnesium alloy or FRP, fiber reinforced plastic. So you can use like alternative to steel and concrete in some special cases when the weight need to be minimized. But the problem is this solution are very expensive. If we look on this figure here, so we have here steel bridge. So as you can see, this all are steel members. And here, this is a concrete or sorry, composite construction. So you have here, this is the steel beam. And this is the steel column. And on top here, this is the concrete slab. And this is a cross section as I have drawn it earlier. So this is again our steel section, I-beam, and this is the slab, concrete slab. And here, this member here is called studs. Okay, so this also some types of composite construction for your information. And here is a Australian standard used for steel design, 4100. So this need to to comply with regulations of this standard. This standard set down the minimum criteria for structural adequacy and provide acceptable method of determining action, forces, and the method of structure analysis and sizing of members and connection. So this standard also cover material and workmanship requirement of the structure, like quality testing and tolerances. This unit is generally intended to be used with the latest version of the standard 2020 AS 4100. So you need to have a copy of it because we will be using it during the course. The second major topic we have is the structural steel framing. So here we will talk about the steel frames. Firstly, the introduction is structural framing comprises all structure member and connection required for the structure integrity. Some common steel building structure we have, like steel single-story dwelling frame, large mill building, low-rise framing, high-rise framing. So all these four are four type of framing, steel framing structures. The design principle of all these structures are almost same or has common principles. Selection, second point is the selection of structure framing element. A wide range of information is required for the selection of the appropriate system. So this is how to select one of the previous system as a system for your structure. So site topography, foundation material, profile, groundwater level, terrain features for wind assessment, access to construction equipment, building layout, minimum headroom and maximum depth of beams, possible location of braced bays for wind again, provision for future extensions, loads exposed on structure like live load, machinery, or crane loads, material used in building envelope and floors, type and extent of building surfaces, ventilation and air conditioning, and fire rating and method of fire protection of the material and the building, means of egress or other statutory requirements. So all these steps or criteria are the main point to select or the main criteria that used to select the best type of structure for your building. And generally, the number of framing elements should be minimized and the weight to be optimized for economic reason. So, and also one of the other points we need to know is this number of frames is often affected by the magnitude of horizontal force, which is related to the height of the building. So when the building is higher, it is more exposed to wind load, so it will affect the number of framing and the design of the building. Structures can be designed to resist horizontal loads. So this are the system for horizontal load, which is mainly wind or earthquakes. So two types of horizontal loads. So the system can resist the horizontal loads are column cantilevered from footing, shear walls, rigid frame, bracing system or straight cables, or combination of the above methods. Okay, these are the systems that can be used to resist the wind or the earthquake loads. The braced frames are one-way or two-way the braced frames are most cost-effective system. This can be one-way or two-way frames. However, the bracing panels often interfere with the functional layout of the building, so the use of rigid frame can overcome these drawbacks. So for example, if we look at a building here, so we might have a bracing bay, but this bracing can affect the functionality of the building, but using of rigid frame can eliminate the bracing and avoid this drawback. In low-rise building, often single-story, workshops, building, and warehouses, the framing system often consists of portal frames in transverse direction and bracing panels in the longitudinal direction. A range of different framing systems are available for tall building where wind load is significantly considered. So for tall building, the most dominant load is the wind load. So Other framing system should be used for tall building, not the portal frame system. So this was the selection of structure framing elements, and now let's start with the mill type buildings. Mill type building, the structure framing for mill type building or medium heavy type industrial building. So this is called mill type. The structure framing for this types of building is usually consist of series of portal frames or bends parallelly arranged, so similar to this type. So this is one portal frame, and this portal frame is repeated. So we have 1, 2, 3, 4, 5, 6. The portal frame is consists of, this is our portal frame. So the portal frame has mainly rafter and 2 columns. And we have here the foundation or footing. So this is the portal frame. These portal frames resist all the vertical and lateral loads acting in their in load plane. So again, if this is our frame, so this frame, so this frame can carry the loads in their plane. Okay, so these green loads are called in-plane loads. So the portal frames can carry these loads. Okay, so this is the first types of load we have. The forces acting in longitudinal direction or perpendicular to the frame out of plane loads are resisted by bracing panel arranges in intervals. So if we look at this photo here, so we might have forces perpendicular to the frame like this. So this forces called out of plane forces and can be resisted by the bracing. Okay, so as you can see here, between the frames here, we have some bracing. So this bracing will resist the, and also here. So we have some vertical bracing and some horizontal bracing. So we have horizontal bracing and vertical bracing to resist the out of plane forces. So now we will talk about the commonly used in-plane framing system. So this frame or portal frame can have different shape. So the first shape is cantilevered column with simply supported roof trusses, as you can see here. So we have cantilevered column. And on top we have assembly supported truss. So lateral loads in this case will be resisted by the cantilever column only. That's why if we look at the column here, this is the bending moment diagram on the column. So if this is a column and it is cantilever, so this will be, sorry. Okay, so this will be the bending moment diagram. Okay, similar to here. So all the wind load will be resisted by the column. Okay, this system, the advantage of this system, it is not sensitive to the foundation movement. So you don't worry about if there is any movement or settlement happen in the footing or the foundation. And this system is relatively easy erection because we have only one pin between the column and the roof trusses. So we have only these pins here. So this is the first type of in-plane framing system we can have. The second type is the rigid joint framed with fixed or pin bases. So if we can have a look firstly here. So this is the second type we can have. So we can have rigid connection here between the column and the rafter. Okay, so we can have three types of this frame. The first one is we have the rafter rigid and the column base is fixed, so fixed base. So that's why the moment on the column will be something like this. So this is the bending moment diagram on the column. The other option is still the connection rigid between the column and the rafter, still same, but the support or the base of the column is pin support. So in this case, the bending moment on this one will be something like this. The third case is similar to second case, but again, we have rigid here and we have rigid connection here between the rafter and the column. Okay, and still the column base is pin. Okay, but here the new thing here is we have a pin or an internal hinge or intermediate hinge here, pin apex. So the connection between the beam at the top of the apex connection is pin. Okay, so these three types of rigid jointed frames we have here. So if we go in details here, the roof members can be rolled or rolled or welded plate section or truss. The frames designed for base fixity rely on the rigidity of the foundation, particularly on rotational rigidity. So this will decide whether it is fixed support or hinged or bent support. So you can decide if it is fixed or bent based on the rigidity of the foundation underneath the column. Fixed based frame, the column is fixed at the bottom, structurally efficient and very economical, but footing are costly. Okay, for the bend frame, the support is bent at the bottom end of the column. So this frames with flexible connection to footing, resisting lateral force through rigid knee action, commonly used in buildings of relatively low span column height. The main advantage of this system is reduced footing cost. So if the cost is not a problem, so fixed will be better. Okay, the columns in the mill type buildings we have are oriented such as there is strong axis parallel to transverse direction of the building, so the building is flexible. If it is not unstable in the longitudinal direction. So if we go here, so if this is our building, so this is our frame here. for example. So the orientation of the column should be like that. Not like that. So if the column orientation like that, this will make it unstable. So this is not correct and this is correct. So again, when you look at the column here, it will be in this direction, not in this direction. Okay, so this is the orientation of the column in the frame, should be like that. So this is for the frame, and also we need some bracing system in this type of structure, the mill type building. So these are some typical longitudinal bracing system for this type of structure. So we can have this type A or this type B. So as you can see here, we have knee bracing system, each 3 or 4 bays. And here, if the height is higher, we can use this system. Both of them are okay. And also on the top, we have some alternatives to the knee system. We can have only diagonal or 2 cross or only 1 cross. Okay, so this is 1, 2, 3, or 4 alternative. And here, if the height is higher, so we can use this number 5 here. So all these are some typical longitudinal bracing system that will be used to resist the out of plane wind. The location of the braced bays should be carefully planned, so obtain the right structure solution, avoid interfering with operational requirement of the building. If possible, bracing should be situated close to the position where the first frame will be erected to facilitate the overall building erection. The bracing in plan of the roof in the roof plan also required to transfer the wind acting on the end walls to the vertical bracing. So again, if this is our building or our portal or framing system, and this is the columns. So we will need to have some bracing. So for example, if we have 2 crosses, so this is called wall bracing. Also on the roof, we will need to have some horizontal bracing. So we need to have wall bracing and horizontal bracing to resist the forces in this direction. So any force perpendicular to the frame will be resisted by the bracing. The roof bracing is usually designed in the form of horizontal trusses or wind girders. So the bracing is considered as a horizontal truss. So for example, if we look at one of them, so this is our bracing system, and this is considered as a truss system. So the bracing system looks like a truss, or we deal it in the structure design as a truss. Okay, and these are some layouts of roof bracing in plan. So this is plan view of the bracing. Okay, do you have any question, guys?
All clear. Thank you.
No worries, thank you. Thank you, Spars. Okay, so this is this figure here, the system of low-rise industrial building. So we have this type, column with truss on top, or columns with rafter on top, and these are the bracing systems can be used for both types, depending on the height and so on. And the next is the portal frames. So if we look at portal frames, the portal frames are single-story structure with rigid beam column connection, such that the original angle between the intersected or intersecting members remain the same. Okay, so for example, if we have this column and this rafter, so what this means is the connection or the angle between the rafter and column was, if it was a right angle, so after the loads are applied to the frame, if the frame rotate, so the column and rafter new position should still be under same or intersect at same angle, which is 90 degree. So this is what is meant by rigid beam column connection. The portal frames are used extensively for framing single-story buildings in warehouses and factories. The portal frames resist vertical and lateral loads through framing action. When fixed bases are used, structure action is enhanced because of all members are fully utilized. So one of the advantages of this system is we used the most of the capacity of the structure element, but the problem is high cost of larger footing often precludes their use. So again, the only problem with the fixed base is the cost. And these are some portal frames connection, the rigid connection between rafter and column. Okay, so A is a field welded connection. B is a lateral bracing connection, and C is a bolted moment in the blade connection. So if we have, for example, like this connection here, so this is the details, and connection D is a stub connection here. So we have a connection in the beam itself. So this is the details of this connection. We have two plates, and this is our member here, and this is our other member here, and this is the connection, stub connection. This is its name. And the next is types of the portal frames. So these are some types of the portal frames for industrial building. So we have A, for example, constant frame. So the rafter and the column are same size. B, we have tapered members. So if you look at the column, the rafter is okay, but the column is tapered. Okay. So the section which here is less than on top. and so on. So these are some types of portal frames. Okay, and for example, K is frame with multiple bays. So we have bay 1, bay 2, and bay 3. So all these are some shapes or forms of the portal frames. What are the advantage of the portal frames? The advantage of portal frame is it's simple in design, and it can cover long span with fast track construction. It has lightweight, and which leads to lighter foundation. No cross bracing are required, so continuous construction. No need to stop to install the bracing. Saving on steel material because it is use the capacity, the full capacity of the member, full capacity of members. More efficient use of capacity of the structure. Less maintenance. Cost effective for short to medium span frames. Advantage over truss system is low structure depth, clean appearance, and ease of coating and maintenance. The next point is how to find the size of the portal frames members. So to find the size of the portal frame members, we need to do so to find the size of the portal frame members, we need to make a sophisticated structure analysis package, for example, microstrand or multi-frame or space case or strand 7, which can rapidly handle the linear or nonlinear analysis. The table below considers only first order elastic analysis based on the Australian standard. So we have two options, like software analysis using any of the mentioned softwares. The other is using the manual or first principle power manual structure analysis. And some of the examples are given here. So you have to calculate the loads, uniform distributed load, and then find the shear, moment, and normal forces, and then design the frames. So for sure, the software analysis will be easier and saving time for the portal frame sizing or analysis. Okay. Also, this link you can watch a video of an example of steel portal frame construction. So you can have a look on this one as well. Do you want to have a rest for 5 minutes and to continue? Are you okay with that?
I think yes.
Yep, sounds good.
Okay. Are you okay to continue on this module until finish and then go to the tutorial questions, or are you okay with that? Just after the break?
Yeah, sure. Yep.
Yes, thank you.
Okay, no. So Barry said you don't like to have a break?
That's fine. Yeah, we can have. Yeah, that's fine. Yeah, thank you. All good.
Or only 2 or 3 minutes, okay? It is now like, because we have already 1 hour, so we can have just a quick break for 3 minutes. Okay. See you after 3 minutes. Thank you. So the next point is steel frame for low-rise building. So what is the steel framing system used for low-rise building? So for low-rise building, we have two-way braced frames and core braced using concrete or steel core with steel gravity frame and simple connection. Or we can have one-way braced frame using rigid framing action in other direction. Or two-way rigid frames with no bracing. So all these systems can be used for low-rise building. And if we look here, this is two-way bracing system or braced frame. As you can see here, we have frame in both direction. If we have, this is X direction, Y direction, this is plane view. So when we have X direction, Y direction. So we have the frames in X direction and frame in Y direction, and the bracing is connecting the frame in X direction and the bracing is connecting the frame in Y direction. So we have two-way braced frames, and also we can have two-way rigid frames with no bracing. So as you can see here, we have again frames in X direction and in Y direction. But because the frames are rigid, so we don't need bracing, no bracing in this system. But here we have bracing, as you can see here. So this two-way bracing, two-way braced and two-way rigid frames for low-rise buildings. And here is the core braced. So in the middle, we have shear wall or concrete shear wall that will make the structure or the frame braced. So this is called core braced. And this is one-way braced frame, but it has also like bracing system in the middle. So this is one way, but braced frame. So the frame is braced with bracing system, not by shear wall. So these two systems are very close, but here the system is braced by the shear wall. But here the system is braced by bracing system or diagonal bracing system. Here, the final option we have for low-rise building is the moment resisting frame. As you can see here, the resisting frame has columns and rafters or beams. The connection between the rafters and the beam are all rigid connections. So that's why it's called moment resisting frame. So the whole frame is working together to resist the lateral loads or the wind loads. So these 5 systems are the main system used for low-rise building, and here's some details on each system. The two-way bridge system and core bridge system are often used for their low unit cost and simple construction. So they are low cost and simple construction. The beam to column connection are flexible end plates or web side plates connection. So the connection between the beams and columns in this system here. The connection here between are flexible connection, flexible end plate connections. This is the main feature of this system. For the rigid frames that featuring a two-way rigidity, so we have two-way rigid frame. This is required more steel materials because you need to make it rigid in both directions. This permit fewer restriction in layout and function. This has less restriction because it doesn't have any bracing or any shear walls. So no shear walls or no bracing. So it has less restriction. Sometimes it is employed in severe earthquake zone due to higher ductility. The other option or the other advantage it has is the higher ductility. So that's why it's used in severe earthquake zones. What are the connections? The framing connection for low-rise building. The connection for low-rise building is oftenly bolted type, so not welding. So the welding is not favored by erectors because for the low-rise building because it couldn't properly carried out without staging or weather shields. Can cause delays in construction, stringent inspection, frequent remedying of defects required because the welding has a lot of defects and so on, so it need to be inspected to avoid this issues. So that's why it is not favored in the low-rise building because it will make delay in the constructions. The next type of buildings we have is a tall or high-rise building. So the definition for tall or high-rise building is a building that can be considered tall when it exceeds 30 story in height. So if the building is more than 30 stories, so it is considered as tall building. If it is less than 30, it can be considered as low or mid-high rise building. So the high-rise building or the tall building start from 30 stories. The engineering definition for tall or high-rise building is when the building structure must resist significant lateral forces, wind or earthquakes, in addition to resisting the gravity loads. So when the wind or earthquakes are very high, so this is considered as high or tall building. Two main design criteria for tall buildings. The first is the lateral forces developed by the wind moment structure. The second is the gravity forces developed by weight gravity structure. So we have two criteria for designing. Again, because the wind is more critical here. That's why it has priority here. So we need to consider the whole building as a moment structure to resist wind. Okay, and we need also to consider it as gravity structure to resist the vertical loads. So if we look here at this figure here, these are the forces on the tall building. So we have gravity forces and we have lateral forces. So two types of loads, the priority for lateral forces and less priority to the gravity loads in this type of structure. So significance of wind load in tall building. In high-rise building, the efficiency of structures can be compared roughly by weight per unit floor area. Weight of floor framing is influenced mainly by floor span, but virtually independent of building heights. So the weight of floor is controlled by the span of the building and not related to the height. The column weight considered only gravity is proportional to the height. So the column weight is related to the height, but the floor weight is related to the span. Building up to 10 stories designed for gravity loading can usually accommodate wind load without any increase in the member side. So up to 10 stories, you can say that the vertical loads are more dominant. So the design for vertical load or gravity load will be sufficient for the wind load. But when you design more than 10 stories, additional material required to resist the wind load, and this increase is nonlinear increase with the height. So again here, more than 10 stories, the wind load will be dominant. Okay, so this is the idea behind the tall story building. For building more than 50 stories, the selection of appropriate structure form is critical for viability and economy. So if we look here and in this figure here, so this diagram shows the significance of weight in the high-rise building. So if we look at here, we have on the horizontal axis the number of floors, and on the vertical axis the weight of the steel structures. So if you can see here, up to 10 here, the gap between the weight of the floor and the total weight is close. But if you see here, for example, so you have, this is the total steel and this is the weight of the floor only. So this gap is just because of the wind loads. So the wind loads will significantly add to the steel cross sections or the steel structure cross sections. So it will increase the weights. Now let's go to what are the structure systems used for tall or high-rise building. So a tall building can be organized with two separated but connected structure system, one to react each different forces dimension, or single structure system can be organized to resist both sets of forces simultaneously. So in the tall building, we can have two systems, one to resist the wind loads and another one to resist the gravity loads. Or we have one single structure system to resist both together. The key goal is structure efficiency. Our goal is to reduce the structure weight. So the main problem of tall building design is the weight. Adequate stiffness is provided, allowing the main frame to be designed as simple construction. So we need to have simple construction with high stiffness. So we can have two types of building or systems: brace system, sway stiffness provided by internal walls, lift shafts, or cross bracing, or unbraced, so sway is resisted by the inherent bending stiffness of the rigid frame action. So we can have two options: braced system. So as you can see here, we have bracing, or this might be if we have a concrete structure, so we might have this bay as shear wall or so on. So this another option is shear walls. So this is called brace system. So the bracing will carry the lateral force. Here in this system, it is unbraced system. So the connection between the rafter and column should be rigid connection to resist the lateral forces. Okay, so this is the two systems can be available for tall buildings. And now let's talk about the development of the tall building. The first step of tall building, or the early tall building, will have steel frames organized to resist gravity loads. A relatively straightforward system of column and primary and secondary beams. This type of frame is efficient at resisting gravity loads. Wind load induced moments are resisted by connection between the beams and column. And again, the old system or the early system was just rigid connection between the column and the beams. So this was how to resist the lateral forces of the wind load, the lateral forces on the frames. Additional strength or stiffness offered by masonry encasement to assist in the carrying moment forces produced by wind. So as you know, these gaps will be filled with masonry or bricks. These bricks will give more stiffness to the system. Making strong structure connection to cope with moment forces increases weight of building with increase in height. So this rigid connection cause increased weight because you need to make a strong connection to resist the wind load. This cause another increase in the weight. This increased magnitude of gravity loads will cause inefficiency and unnecessary cost. So more weight means more cost. So again, this is a explanation of some old skyscrapers or old tall buildings. So the system again was very simple system, and the connection between the column and the rafter was rigid connection. And the whole system together resists the wind load or lateral forces. So the next or the advancement in tall building cause or advice to use frame and core approaches. So the frame and core approaches cause shear truss frames. The truss resists moment lateral forces, and the frame resists the gravity forces. So for example, same system above, we can have in the middle some bracing system. So this bracing system is resisting lateral force and the frame resisting the gravity force. This system has also some similar system in concrete, which is can have same system but in concrete using a reinforced concrete shear wall, RC shear wall in the middle. So both systems are similar. The wind load are resisted by the bracing or the shear wall, and the gravity loads are resisted by the frame itself. So in the frame and core approach in concrete structures, the shear wall resists the moment and the frame resists the gravity force. Truss or core resists the moment force instead of relying on the connection between the column and the beam. So the connection are designed primarily around the gravity forces. So this removes the weight from the structure because you design weaker connection because it doesn't resist the moment. Removing weight improves the efficiency of the structure and reduce the cost. These factors allow greater heights to be reached for the same cost or the same width of the structure. So using the bracing system or the shear walls in these two cases, like reduce the cost and increase the height. Okay, so these are the bracing elements to resist the wind. And here we have reinforced concrete shear walls or shear wall to resist the wind. So this the advanced or the modified system to avoid the weight, the additional weight or the excessive weight due to the connections. So you might have some other advanced system for taller building. For example, there is a system called outriggers and belt trusses. So in this system, we have, this is a cross section of the building. So we have RC core and we have some trusses. These trusses are surrounding the building or outrigger the building. So this system can reduce the weight of the building and also better resistant to the wind load. So if you can have a look here. So this is 3D view of the system. So we have the core in the middle and we have the outrigger system. We might have 2 or 3 of them. So this makes the whole building work together to resist the lateral forces. Another system we can have is the tubes or bundle tubes or tube in tubes system. So in this system, we have like tube surrounding the whole building to resist the wind load. So this tube works a system to resist the wind and also resist the gravity together. So this makes the structure more stiff and more able to resist the forces. Another or a modified system is tube in tube system, which is more stronger than the tube system, but is again same concept. It resists the wind load and also the vertical load together. Or the third one is the bundle tube system. So it has several tubes together to resist the wind load and the gravity loads. So all these systems are systems used in modern construction for tall building or high-rise building. The final topic we'll have today is other structural steel element, which is used for long span structure. In some cases, you might need to use like untraditional systems for long span structure where we don't need 2 columns for architectural requirement as an example. For example, in like cinemas or lecture halls and so on. So we need to have large opening spaces are required for sometimes required for functionality. Using of blade girders or trusses, space frame, arches, or even cable suspended roofs as beam to support large or concentrated loads. For example, mall roofs or hotel ballroom floors. So for example here, if we have this buildings and we need to have no columns in the first story, so this red element should be very strong element. So for example, we can use plate girder. A plate girder might be a very deep plate, which is not available in the market, welded to two small or two flanges. So the depth of this beam, for example, 2 meter or 3 meter, to be strong enough to hang over this span. So this is one of the example of the plate girder, which is this welded flanges. So like 3 plates, 1, 2, 3 plates welded together to form a huge or bigger section. So the plate girders are deep beams used to carry large loads over longer span. It is a built-up beam, so built-up means welded together by welding steel plate together, forming I section. Used in long span floor girders, heavy crane girders, and bridges. Support bending moment larger than the moment capacity of available rolled sections. Top and bottom flange resist bending moments. So the top and bottom flange resist bending moments, and the web resist shear. Moment capacity can be significantly increased by increasing the distance between the flanges, but the slenderness of the web is also increased, thus reducing buckling capacity. So when you increase the distance between the two flange, D, the capacity increase, but the problem will be the buckling. Intermediate stiffener are required to prevent the buckling due to bending or shear. So if we have this section here, so if you increase D, the section capacity will increase, but buckling will be a problem. So to avoid buckling, what we need to do, or what we need to add, we can add stiffeners. These stiffeners will reduce the buckling of the cross section. Tension field action is utilized to increase the shear buckling resistance of thin web. Stiffeners are required at load point and supports. So we need to add stiffeners at the point, load, and supports. Okay, so for example here, this is an example of plate girder. As you can see, this is the top flange. This is the bottom flange. And here is the stiffeners. As you can see, stiffeners are needed at the supports or at the reaction. And also there is a distance between the stiffener is called S. So we will learn about this later. But you need a stiffener at least at the supports and under the loads. If you look here on this bridge, this is like bridge beam. So the bridge beam has also plate girder. This plate girder has, as you can see here, some stiffeners at the supports. So all these examples are example of plate girder, which might be needed for long spans with higher loads. Okay. Do you have any question regarding this regarding this lecture, guys? Any question?
No.
No, all good.
Okay, thank you. So now I will stop sharing this one.